Yeah. Welcome, everyone. So today we are very happy to have Suvrat Raju from the Tata Institute of Fundamental Research. Today he's going to talk about his recent work on quantum gravity. Please.
Thank you very much for having me over and as I said, for waking up early. So I'm going to speak to you today about this work on holography of information and massive islands. It's work that I've done with a very large number of collaborators, so I should start by just acknowledging them. So some of the story that I'll talk about was started in this paper that we wrote with Alok, Siddharth, and Pushkal last year, and then a follow-up with Chandramoli and Olga. And then a couple of papers we wrote with what we call the group of 7, which is How, Andreas, Carlos, Lisa, Marcos, and Sanjeev. And then this more recent paper with Chandramoli, Victor, and Olga. And some of this is reviewed in this paper from last December, which is like a longish review. So if you'd like to look up more details. So, I know this is like a broad audience, so I thought I would just start by giving you a general introduction to what I'm going to talk about. And so I thought I'll just spend maybe 10 minutes just showing you some pictures and giving you like some non-technical introduction to various things. And then after that, I'll say, I'll try and say things which are more precise. So that's the first part, and then I'll talk about this notion of holography of information in flat space and how it follows from the Wheeler-DeWitt equation, the implication for black holes and for islands. So let me start with this overview and intuition section. So, the title of this talk is the holography of information. And the theme that's going to run throughout this talk is the following. It's that in quantum gravity, information that is present in the bulk of a Cauchy slice is also available near its boundaries. So, if you think of this as a slice, and you have some bits or some qubits that are living here, then there is some way to extract that information just by making observations at infinity. Maybe you need to make very difficult observations or very complicated observations, but there's some way to extract that information from infinity. And that's a principle that I'll try and claim holds in EDS, in Minkowski space, and it will be the theme that will run through this. So let me just try and explain why that's significant and explain the contrast with ordinary quantum field theories. So in ordinary quantum field theories, there's something that we kind of take for granted. And it is that we think we can prepare states where you have some excitation, that's this bump on this side, and everything outside looks exactly like the vacuum. In fact, such states have a name, it's called split states. But it's something that we just take for granted. You act with some unitary operator which is bounded and in some compactly supported, and you create an excitation in some region, and for an outside observer, there's absolutely no difference than if you would be in the vacuum. And what is more, we think that we can change the form of the excitation. So instead of this bump, I could have a bump of this kind, and I could still keep everything for the outside observer unchanged. So this is something that we take for granted in QFT. What I'm going to try and tell you is that in gravity, this is not the case. And first of all, you can't even set up a state like this where you have an excitation and everything outside looks exactly like the vacuum, because you have to have some tails that go off to infinity. But then I'm going to say something that's slightly stronger. If you were to change the form of this excitation in the middle, so you change it from this kind of a bump to this kind of a bump, then you also have to change the tails. And in fact, the tails are in one-to-one correspondence with this excitation, and there's no way to change the state inside a bounded region while keeping everything outside the bounded region fixed. So that's the difference between gravity and quantum field theories that I'm going to try and explain. Let me say this in a way that's even more dramatic. Although I won't talk about the operational procedure, this was the subject of this paper that we wrote with Chandramoli and Olga. You see, imagine that you have some excitation or something, right? Maybe a rugby ball or a football or something in the middle, and you have a web of detectors that surrounds it. So every place in latitude and longitude intersects, you have some detector, and you want to find out what's the shape of this ball. Is it an ellipsoid? Is it a sphere? Is it a football or rugby ball? Or is it red or is it orange or something like that? And in a usual quantum field theory, you would need to wait for the for light from this ball to emerge, and so you need to wait for the light crossing time of the sphere in order to be able to answer these questions. The implication of what I said about how gravity localizes quantum information is that in gravity, this information is just always available outside. So these detectors need to switch on, and they always have the information, and they can switch off immediately after an infinitesimal time interval. It might later take them time to process this information. Maybe this detector needs to communicate with that detector and so on. But the detectors don't actually need to be on for the light crossing time of the sphere. And that's a very sharp difference with usual quantum field theories. Okay, so that's, I'm just trying to emphasize the difference. So that's going to be the theme of what I'm going to say. Okay. Now, why would you believe even, so I'm going to try and give you a cartoon argument for why you would believe even that gravity has, some property like this. So I'll give you a cartoon argument, but actually, as I'll try and say later, the argument is not actually that much of a cartoon. It actually works, even though right now what I'll say will not be precise enough to dot all the I's and cross all the T's. But I'll show you later how one can actually realize the intuition and present it. So let me go back to something that we learned in our childhood, which is the uncertainty principle. And the uncertainty principle that we learn as in our childhood tells us that if you have some wave function that's sharply localized in momentum space, it's completely delocalized in position space. And in relativity, a momentum comes together with energy. So if you think of a wave function that's sharply localized in energy, and I'll tell you why I'm referring to energy in a minute. If you think of a wave function that's very sharply localized in energy, it's completely delocalized in position. Okay, so that's fine, but that doesn't prevent us from creating local excitations. You measure some particles at the LHC, the particles are measured in some detector. I'm localized here, all of you are localized somewhere else. And so how do we create localized excitations? The way we usually do it in quantum mechanics is you take one of these, these states, these wave functions, which is peaked at a given energy. You add to it a wave function that's peaked at a different energy with the right phase. You add to it a third wave function, which is peaked at a third different energy with the right kind of phase, and so on. And if you add an infinity of such wave functions in the right kind of way, then you can ensure that all of these wave functions interfere destructively outside some bounded region, and they interfere constructively inside the bounded region. And doing that, you can create an excitation in position space of the kind that I have on the right-hand side, which is a localized excitation. So that's what we do in quantum mechanics, and that's also what we do in quantum field theory. It's precisely the same procedure. If you want to create a localized wave packet, you take an infinite number of energy eigenstates and you superpose them in the right way. And if you do that, you can create localized wave packets. And that's how you create localized excitations of the kind that I was talking about earlier. Okay, so why can't you do this in gravity? Why would you think that this procedure would not work in gravity? So the first thing is that gravity is kind of special because it has a Gauss law. It has a Gauss law, and the Gauss law, just tells us that we learned it even before the uncertainty principle. It just tells us that if you have some mass and you go off to infinity, you can measure the mass at infinity just by looking at the fall off of the gravitational field. In fact, there is a precise formula for this in general relativity, and that's the formula that's up on your screens. It's called the ADM Hamiltonian, and tells you that if you want to measure the energy inside some space-time, what you should do is Minkowski space in a similar formula in EDS. But in Minkowski space, you go off to infinity and you measure the subleading components of the metric and you integrate them with the boundary sphere, and that gives you the energy. In fact, this is the definition of the energy in general relativity. So we don't have a local definition of energy in general relativity. This is the definition. This is also the definition of the energy in the quantum theory. Okay, so there's a Gauss law in gravity, and why is that special? Why does that change anything? So the reason it changes things is because let's go back now to our excitation, which was peaked in energy, which had some fixed energy. And now you see that because of the Gauss law that I told you, this excitation has to have a tail, and the tail has to go off to infinity. So the tail has to go all the way out to infinity. So this excitation is delocalized in position space, but it has to have together with it, some component of the metric. You have to dress it correctly with the metric, and that dressing has to go off to infinity. Okay, and now let's say you tried to play the same game that you played in quantum field theory, which is you try to superpose a number of these energy eigenstates in order to create a localized excitation. And if you think about what would happen, you see, you would start with some energy eigenstate at some energy, and that has a particular tail, and that tail is actually a full degree of freedom. So there's some particular excitation or state of the metric that corresponds to that. And then you add to it an energy eigenstate with a different energy, and that corresponds to a different tail. So if you think of the big Hilbert space of the states of the matter and of the metric, you actually have to have the valid states are these entangled states, the states that obey the constraints. And those are these entangled states where you have to entangle every energy eigenstate with some particular tail. And every energy eigenstate has a distinct tail that comes along with it. And these tails are a full degree of freedom. And so if you do now try and play the game that you had previously, where you try and superpose these energy eigenstates together so as to have destructive interference outside the bounded region, you find that procedure fails, and these tails don't interfere destructively because of their form that the states have to take in a theory of gravity. And I emphasize that it's not just the energy that carries information about the state, but rather it's correlators of the energy and other observables that carry information about the state. So you might have two different energy eigenstates which are exactly degenerate, but as I'll show you, correlators of the energy and other observables always retain information about the state. So this is, of course, a cartoon argument, but I've told you right now is not a proof. But this is, in fact, the intuition that will turn out to be important in what I'll say, and also when we discuss islands. And it's just this very simple fact, which is that, when you think of states in the theory of gravity, the matter sector has to be entangled together with the metric. And this entanglement is such that you can't have destructive interference outside the bounded region, or while having constructive interference inside it. Okay, so that's going to be the intuition that I'll find very
interesting. Yes, interrupt just a minute?
Of course.
Yes. Sorry, this goes back a little bit, just a clarification. When you said that all the information is on the boundary, were you referring to pure gravity theories or with matter content?
No, so you could think of pure gravity theories, or you could think of gravity with matter. So if you had gravity with matter, there would be some dynamical degrees of freedom, which would be the transverse traceless gravitons. There would be some constrained degrees of freedom that you see on the right-hand side. So for the purposes of this argument, it doesn't matter much. Of course, we don't think pure gravity theories are consistent in some UV way. So presumably you'd have to add a lot of matter to make the theory consistent. But for the purposes of this argument, it doesn't matter whether you have pure gravity theories or gravity coupled to matter. In general, in many of the examples I'll give, I'll use scalar fields as an example of matter, because matter will not matter.
So that confuses me a bit, because you said that in non-gravitational theories, the boundary does not contain all the information.
Yes.
In gravitational theories, all the information is contained on the boundary.
Yes. Yes.
I see. So I was just confused that when you meant gravitational, you were including matter content in it. So somehow including gravity also makes the matter behave as if it was all on the boundary.
Indeed. So that's why. So correlators of the gravitational degrees of freedom and of the matter degrees of freedom now carry information about the state. So there are tails which are gravitational, but as I'll show you, you're right. So you have a new set of correlators now in the theory, which are correlators where you can have metric insertions and the matter insertions, which didn't exist when you had only matter insertions.
I see.
So if you keep track of only matter correlators, then of course you don't have the information. But you keep track of this new set of correlators, you will have the information.
Okay, thank you.
Okay. Great. Okay, so let me first try and give you a precise argument.
Hi, Suvrat. Can I interrupt again also?
Yes, sure. Yeah.
I just want to understand that statement you just made about.
Yes,
ENM, of course, also has Gauss's law and also has a massless field. So how would it differ there?
Because you have neutral excitations in ENM. So there is something like an exactly local gauge invariant operator. You take trace of f squared, and you don't need to dress it to anything. It doesn't need to have a tail. Trace of f squared is just an exactly local gauge invariant operator. So the difference in what I'm saying is that you can have both positive and negative charges. The tails don't need to go off to infinity. You take a positive charge and a negative charge, you dress them to each other, and you don't need to have something that goes off to infinity. So gravity is different in that way for this reason. Because the
So
charges are only positive and you don't have them.
it's different because the masses are always positive. Is that the difference?
Yes, because masses are always positive, and that's the reason you can't, you can't dress a positive mass to a negative mass to make a local gauge invariant operator as you could in a gauge theory.
I see. Okay, thanks. And one more comment: if gravity
Yes,
were
please.
massive, if there were massive graviton, then the statement wouldn't be true, right? Because there would be.
Yes, the statement would not be true. So indeed, I'll talk about that towards the end of the talk. In massive gravity, you would not have a Gauss law, so this would not be true.
Yeah.
Okay, thank you. Thank you for the comments. So let me now first try and make this argument precise in flat space. So I'll give you an operator theoretic argument, and then I'll say give you other ways of looking at this. So let me first give you what I think is the most precise argument we have for this statement. So the argument works in 4-dimensional flat space, and the statement is, so I'm not saying the cartoon, I'm saying trying to make a precise statement. Statement is that I'll now consider 4-dimensional flat space a theory of gravity with matter, but only massless matter for technical reasons, although we can say a little bit now about massive matter, but for now I'll just talk about massless matter. So if you have massless matter, then the claim is that in a non-gravitational theory, to get information about the state of the theory, you would need observations on all of Scri plus or on all of Scri minus, but let's just talk about Scri plus because everything I say on Scri plus is an analog in Scri minus. You would need to make observations on all of Scri plus in order to determine the state of the matter field. But in a theory of gravity, I'll say that the information is in fact available near the past boundary of Scri plus, which is this little red region that I've marked here. Or equivalently, it's also available near the future boundary of Scri minus, which is this orange region. But as I said, to avoid duplication, I'll just talk about this, Scri plus. So this is another view of the Penrose diagram in one higher dimension. And the claim is that rather than having to make measurements on all of Scri plus, you can make measurements only for this little red region. Okay, so how would you come to a conclusion like this? So I'm going to sketch for you the argument. I'll go through it fast, and then I'll give you other ways of looking at it. So first, just to explain the setup, we're just interested in 4-dimensional asymptotically flat spacetimes with very standard boundary conditions. So this is something that's been studied now for many years. What you say is that you have some metric. The metric can do whatever it likes in the bulk. But if you go off to infinity, then you demand there are certain fall-off conditions. In particular, you demand in the so-called Bondi gauge, the metric looks like this to leading order. And then there are other subleading terms in the metric. These terms, CAB, or actually the derivative of them with respect to U, is what's called the Bondi news. And then there are other constrained degrees of freedom still describing fluctuations of the metric. This is called the Bondi mass. It's just one of the subleading degrees of freedom out at infinity. And then you might have other matter fields, and you take the subleading tails of those matter fields as well. And those are also observables at null infinity. Now, what I'm going to try and tell you is that, in fact, all this information is available in the algebra of observables near the past boundary of future null infinity. And what that means is that you take these observables and, as is usual, you take all possible products and linear combinations of these operators, but for the retarded time being in this range from -infinity to -1/epsilon. And I'll say that this algebra, which in a non-gravitational theory would be a small subalgebra of the full algebra at Scri plus, in fact has all information in a gravitational theory. Okay. So let me first also review a little bit about the Hilbert space. So this Hilbert space of 4-dimensional flat space in theories of gravity has been studied a lot in recent years, or going back in fact to the work of Hashtaker, but then more recently the work of Strominger and Strominger's group. And it's been studied a lot. And one thing that we learned is that the vacuum is infinitely degenerate. And the vacuum is labeled by the so-called supertranslation charges. There's an infinite number of supertranslation charges. And to specify the vacuum, you need to give me the value of all of those supertranslation charges. This, in fact, is a technicality. It's something that we need to, it's an obstacle for us, but that's just how it is. And then on top of each vacuum, we build a familiar kind of Fock space. The reason it's a Fock space is because when you're quantizing at null infinity, all the interactions have switched off. And so you build a Fock space, and the graviton Fock space is just taken by taking these news operators and smearing them with the right test functions and acting on the vacuum. And if you had other matter fields, you would do the same. And that would give you, the usual construction of the Hilbert space at null infinity. So now I'm going to sketch for you why in the theory of gravity, all information or all operators in this space, in fact, can be approximated arbitrarily well by operators from this algebra near the pass boundary. So there are 3 steps in this proof, and the first step is to recognize that if you take any element of this Fock space, you can I showed you how I said you generate the Fock space by taking the news operator and smearing it with test functions on all cos square plus. But in fact, it turns out that if you take the news operator and smear it with test functions only near the pass boundary of infinity, that is enough to approximate any state arbitrarily well. And this uses only the positivity of the Hamiltonian. In fact, this is a version of what's sometimes called the Riche-Leader theorem, although we use it in we've proven a version of it at null infinity. And this Riche-Leader theorem is something that requires only the positivity of the Hamiltonian. And it's in fact also true in a non-gravitational theory. So this is a theorem that also works in a non-gravitational theory. And then in a theory of gravity, what is special is that it turns out that the projectors onto vacua, these infinite number of vacua that I described, are also elements of this algebra A minus infinity. Now, the reason that is the case is because, in the theory of gravity, there's a very special property, which is a property that I alluded to earlier, which is that the Hamiltonian and the supertranslation charges are given by boundary terms, and that follows from the Gauss law. As a result, you can project onto the vacuum because you can have a procedure where you measure the Hamiltonian and you discard the state unless you get 0. So you can use that to project onto the vacuum and also project onto a particular vacuum by selecting also the supertranslation charges. And so there's a very special property of gravity, which is that the projector onto a given vacuum is an element of this algebra near the pass boundary of future null infinity. And this, I emphasize, is the key property of gravity that makes it differ from other non-gravitational theories. And then there's a third element that you need, which you can just check by direct calculation, which is that not only the projectors onto the vacua, but all operators in this vacuum manifold are elements of this algebra A minus infinity, which one can just check by direct calculation. And if this is the case, then you see that any operator in this Fock space, you see can be written, obviously can be expanded in terms of a complete basis of states, where you take one element of one Fock space that's built on one supertranslation vacuum, another element of another Fock space built on another supertranslation vacuum, you just expand the operator in a complete basis of states. And then using this first Riche-Leader result that I mentioned, you can write any operator in this form as an action of an element of this algebra A minus infinity on a vacuum, and as the action of another element of this algebra A minus infinity on a different vacuum. I emphasize that everything I said so far would also be true in a non-gravitational theory. But now in a gravitational theory, what is special is that this operator that appears in the middle, which is ket s bra s prime, is also an element of A minus infinity. And therefore, everything that appears in the expansion of this operator is an element of this algebra A minus infinity. And since the algebra is closed under products and linear combinations, any operator that takes you from this Hilbert space back to the Hilbert space can be approximated arbitrarily well when operator is prime plus minus. So that's a sketch of the proof that we, of the proof that all operators can be approximated arbitrarily well by operators S prime plus minus. And I emphasize that the key point here is that these vacuum manifold operators are elements of this algebra A minus infinity, which happens because the Hamiltonian and the supertranslation charges are given by boundary terms.
Quick question, Suvrat. I'm a little rusty,
Yes,
but would you have any quick comments on how your proof relates to say things like gravitational wave memory effects?
How does it relate to gravitational wave memory effects?
Memory effects.
I'm not sure. Can you make that more precise? Like in a so,
well, so if I remember correctly,
yeah.
you can talk about soft theorems, supertranslations, and how they relate to gravitational memory, right? And that seems to be sort of part of what you're talking about. So
I mean, so memory is the fact that you have some set of masses of test charges. You have a wave that goes through them, and that takes you from one vacuum to another vacuum, and you can see that. Right? So I mean, there are these vacua, and maybe these operators which transition you from one vacua to another vacua are the kinds of operators you're talking about when you talk about memory. But memory is a classical effect, whereas what I'm talking about here is not a classical effect. I mean, none of these statements would be true classically. So I mean, it's true. These operators that take you from one vacuum to another vacuum are the operators you talk about when you talk about memory. You're transitioning from one super translation vacuum to the other one. But I don't know if that's what you had in mind.
That is something to the extent sort of what I had in mind. Yes.
Okay.
And
so,
also
I mean,
because how you have
yeah.
differences in large gauge transformations between gauge theories and the BMS group being thought of as the equivalent of those large gauge transformations to take it from one vacuum to another in gravitational theories. And anyway, I'm going to stop because I'm blabbering now, but thank you.
Okay, thank you, Yash. Okay, let me now try and give you another perspective on this argument.
Actually, Suvrat, sorry, can I ask one more question on the previous slide? I don't know if I need the slide, but I think all the things you're talking about here are just the super translation set, not the super rotation set. Is that correct?
Yes.
Super rotations also included.
Thank you. Yeah, I did not need to use the super rotations here. The question is whether vacua are labeled only by super translation charges or also by super rotation charges. So, the understanding is, at least in the literature currently, is that, if you take the set of all super translation charges, that labels for you already all vacua. So all that was important here was that. Now, if it so happens that we find that, you need additional labels for the vacua are not specified uniquely by super translations. And what would be important is that the charges that specify the vacua are still boundary terms. So we don't think we need super rotation charges to specify the vacua, but if you did, the super rotation charges are still boundary terms, and that they're still defined as square plus minus, and so it would still be okay.
Okay, thanks.
Thank you. Okay, so I gave you some operator theoretic argument. That's actually the most precise argument that we have, and we can use it also in ADS, but it's a little formal, and perhaps some of you are thinking, you gave me this operator theoretic argument, but maybe there's some subtlety. I don't believe it. What if I just try and write down this wave functional of this form below, right? I had in the beginning this slide where I said, in quantum field theory, you can prepare these wave functions which have excitations and look like the vacuum outside, and someone will say, look, I'll just write down the wave functional like that in gravity, and what prevents me from doing that? In fact, we have been asked this question, right? So there's some operator theoretic argument, maybe something is wrong with that. So I'll now give you a different perspective on the same story. The different perspective has the advantage of being a little more explicit, but it works only in perturbation theory and only with ADS boundary conditions, but it might help to elucidate the physics of what's going on. So the reason, of course, you cannot write down wave functionals like this in a theory of gravity is that not all wave functionals are valid wave functionals. In particular, in the quantum theory, there is a set of constraints that we've known for a long time. And the set of constraints that wave functions need to satisfy go by the name of the Hamiltonian constraint and the momentum constraint. And the Hamiltonian constraint is called the Wheeler-DeWitt equation. So valid wave functionals need to satisfy the Wheeler-DeWitt equation, which roughly tells you, they need to be, there's a gauge redundancy in the theory of diffeomorphisms, and these wave functionals need to be invariant under diffeomorphisms that move you up and down in time. And these momentum constraints have to do with spatial diffeomorphisms. They're kind of easier to solve. And so the Hamiltonian constraint is the important one. And not all wave functionals are valid. So in fact, what one can prove is the following statement. This is a perturbative statement. It's more explicit, but has little less, a little less range than the previous result I showed you. That if you take two solutions of the Wheeler-DeWitt equation in ADS that coincide at the boundary for an infinitesimal amount of time, then they must coincide everywhere in the bulk. So that's the statement that the boundary value of the wave functional for a very small amount of time completely fixes the bulk values of the wave function. And that's why you can't create states which, you have excitations that have to do something in the bulk, and the boundary looks exactly like the vacuum. And I want to emphasize that, if from the point of view of ADS CFT, this is kind of an obvious result, because the boundary data at a single instant of time, you don't even need an infinitesimal amount of time, completely fixes the bulk state. But this doesn't assume ADS CFT. One can think of as establishing a perturbative version of holography for gravitational theories, explaining why it is that gravitational theories are holography.
Why was it necessary
so,
for this to be ADS then?
It's for technical reasons because of infrared issues. In the absence of, if you're in a flat space, then the argument that I'm now about to give you, wouldn't work so well if you had a continuous set of vacua. In global ADS, there's a unique vacuum, so it's easier to make this argument. This argument I'm giving you right now is a perturbative argument. The previous argument, we were able to surmount these IR issues, but we don't know how to surmount these IR issues with this WTW argument. So it's a technical obstruction. Does that answer the question?
Yes, thanks.
Okay, so now of course the relativity equation has been known for a very long time, but something we found, maybe is that perturbative analyses are there, and there's some older work by Kuchar and some follow up to that, but mostly people haven't looked at perturbation theory. It turns out it's pretty productive and fruitful just to look at the relativity equation and perturbation theory. So we do something pretty simple. We take the metric and you expand it about background ADS, and we expand it about background ADS, and so there's some background global ADS metric, and then there are additional the fluctuations of the metric, and you can divide these fluctuations into transverse traceless fluctuations, longitudinal fluctuations, which is just pure gauge and a spatial slice, and another set of fluctuations which keeps track of the trace, which we call the T component, which will actually be important as we go forward, which is also transverse, but has the trace. So that's just a decomposition of the fluctuations of the metric into three parts. But these will turn out to be the dynamical degrees of freedom. This is what we use to satisfy the Hamiltonian constraint, and this is what one can use to satisfy the momentum constraint, the longitudinal. Okay. So we found that there's something very simple, which is that the Hamiltonian constraint is in fact an infinite number of constraints. It's not a constraint at one position. It's a constraint at every position. But it turns out that it's very convenient to look at a particular integral of the Hamiltonian constraint, which we call the integrated constraint, which is you just take the Hamiltonian constraint and you integrate it with some particular Laplace function. And if you do that, we found that this Hamiltonian constraint takes the following form. The details of the equations are not important, but let me just say in words what is important. It relates some quantity that you would think of as the bulk energy in ADS, which depends on the transverse traceless graviton and the matter degrees of freedom, and looks like a Hamiltonian, like a bulk Hamiltonian. It relates that to something that depends on only this T component. Only the T component. So we don't even need to assume that the Hamiltonian is a boundary term. We just take the Hamiltonian constraint, and if you integrate it, that forces you to this formula that tells you that the T component, some component of the metric at infinity, gets related to some integral of some other component of the metric and matter fields. And that's just a Hamiltonian constraint that wave functionals need to satisfy. In fact, if you go back to the cartoons I showed you at the beginning of this talk, this is the precise version of that cartoon. It's the statement that any state, there's some energy density integral that gets related to some tail of the metric at infinity. Then we can actually solve this integrated constraint explicitly. We are able to write down these solutions to the constraints. And the solutions to this integrated constraint look pretty simple. And the way they look like is that you take, in perturbation theory, just some Fock space for the transverse traceless gravitons and the fields phi. Here it's a Fock space just because we are working in perturbation theory and the matter fields. And you entangle it with, by putting this boundary degree of freedom, this integral of this T component in a particular state. So, this is the realization of this cartoon I was showing you earlier, where a matter excitation in the bulk gets entangled with a particular kind of gravitational tail. And so you see the constraints of the theory force correlations between boundary degrees of freedom and the bulk state. Now, as I said, there's an infinite number of other constraints in the theory because we used only a particular integral of the Hamiltonian constraint. But what the other constraints do is they just lift every solution of the integrated constraint to a solution of, of the full set of degrees of freedom. So they fix the remaining dependence on these HT and HL variables. But the important one, the important structure is already apparent in these solutions to this integrated constraint, which is that there is this entanglement between these bulk states and these boundary degrees. In fact, after that, it's pretty easy to construct the rest of the proof. We take an arbitrary mixed state in the theory. This is just taken by the solutions of the Wheeler-DeWitt equation. You multiply it with its conjugate, you sum over an arbitrary set of states. And then we need to impose the equality of a particular set of boundary correlators. This particular set of boundary correlators is this integral of this T component that I was calling edge boundary raised to the power n, and then insertions of dynamical degrees of freedom for a small time band between 0 to epsilon. So this entire correlation function that appears on the left-hand side is some correlation function at the boundary for an infinitesimal amount of time. And it's pretty easy to show that if these correlators are equal for an infinitesimal amount of time, then these states must be equal. So if you take two states of this form with different coefficients, the only way you can make them coincide for an infinitesimal amount of time with the set of correlators is if the states themselves are equal. And this is, in fact, the realization of the physical intuition I was giving you at the beginning, that if you look at solutions to the constraints where you have some bulk degrees of freedom that are entangled with some boundary degrees of freedom, and you try to engineer destructive interference outside of bounded region and constructive interference inside, one can't do that. And one can see this very explicitly in the structure of the solutions of the Wheeler-DeWitt equation. Okay, so that is another version of what I said. If there are questions, I can stop here. I'll now go on to talk about black holes and other things. Okay, maybe we can come back if there's questions. Let me now say a little bit about the implications of the story for black holes. So that's first of all a cartoon version of the implication of the story for black holes. What I've been saying so far is that if you have some state in the Cauchy slice, that the state is imprinted also on the boundary of the slice. What that means is, in particular, that if you take a black hole state, then information about this black hole microstate is always available outside with the right kind of measurements. So if you have a set of observers, who make the right kind of measurements outside, then these observers are able to determine what the microstate of the black hole is at all points of time. So notice that there's something very different about the quantum theory and the classical theory. In the classical theory, there's an O'Hare theory. It tells you that what the observers can see outside is only the energy. But in the quantum theory, the state is of the black hole is a superposition of these different energy eigenstates, as I said at the beginning. And if the observers outside have access to correlators of the energy and of other matter fields, they can determine what microstate there is in principle. Of course, this is a non-perturbatively difficult computation to do. So these observers will have to make extremely accurate measurements outside in order to determine what the microstate of the black hole was. But the arguments that I gave you previously give you a proof in principle that the observers could always do this. And there's a more formal result of the proof. It goes back to this to flat space. So here's a Penrose diagram of an evaporating black hole, and using the operator theoretic argument that I gave you at the beginning, which, as I said, is the most precise argument that we have, one can ask the following question. One can define the phenomenon entropy of a segment of null infinity, this red segment, and one can ask, what is the phenomenon entropy of the segment? How does it vary as you go up in an evaporating black hole state? And one can show, in fact, that this phenomenon entropy is independent of the upper end of the segment. So it stays constant as a function of u. And that is the precise version of the statement that the information is always outside. And that's a result that can be proved. I mean, it follows kind of obviously from the results I told you previously, which is that if all information is available near the pass boundary of your general infinity, then it's clear that as you go along further, you do not get any more information. Of course, this contradicts Hawking's suggestion that the entropy should rise monotonically. So Hawking argued famously that if you take an evaporating black hole, then the entropy of the evaporating black hole will just rise monotonically. So why does this result that we have differ from the result that Hawking had? And in fact, it's not hard to trace the difference. There are two. Sometimes the question that people ask is, what is the error in Hawking's argument? Why do you get a different answer? And in fact, it's not hard to see why we get a different answer. So first, of course, when Hawking made this original argument, there were two aspects to the argument. There was a computation and there was an argument. So the computation of Hawking was in fact to compute the final state at null infinity and to compute the occupancy of square plus, of modes at square plus. And he found that this occupancy was thermal. But in fact, this calculation by itself does not amount to a computation of the entanglement entropy, because if you were to add to it the right kind of exponentially suppressed corrections, then this result would also be consistent with the final state being pure. If you take a pure state, a generic pure state in a big Hilbert space, all correlators do look thermal up to exponentially small corrections, which Hawking didn't control. So these low point correlators that Hawking computed cannot really be used to conclude that the final state is mixed. So Hawking did a little bit more than provide this computation. He in fact provided an argument to suggest that the computation was robust. And the argument was based on what Hawking called the principle of ignorance. And this was the following statement. So Hawking argued that if you take a black hole, and he said you have to introduce about every black hole a hidden surface, and then the observer outside this hidden surface in our modern language, you could just think of, if you take a nice slice as a part of the the state inside the horizon. And Hawking argued that the observer outside would need to sum over all field configurations of the hidden surface, because the observer outside is space-like separated from all excitations inside. And then he assumed that he said a basic assumption of quantum theory, you see on the left-hand side, this is really a quote from his paper, is that the Hilbert space should factorize. You should be able to write a factor corresponding to the hidden surface and a factor corresponding to the degrees of freedom outside. And then the observer outside needs to trace over all observations in the hidden surface, because the observer outside has no information about them. And if the Hilbert space does factorize up to a few global constraints imposed by the no-head theorem, then indeed it would be the case that the state outside would be thermal. So this was Hawking's argument to suggest that even though the computation he did was a leading order computation, because of this causal structure and the fact that he assumed that the Hilbert space would factorize, this would be enough to argue that the final state would be mixed, even if it was mixed in a slightly different way from the precise computation that he did. But the previous discussion that we had showed that this fails in a theory of gravity. It's not true that the Hilbert space factorizes. It's not true that if you set up excitations in the hidden surface inside, that you can do so while leaving no imprint outside except for the total energy. And as a result, if one asks, where is the error in Hawking's argument? The error in Hawking's argument is here. It's in this line where he assumes a factorization of the Hilbert space, which one can explicitly show is false. And in fact, it's the opposite of what Hawking said. It's rather than having a principle of ignorance, there's a principle of information that says that excitations in the hidden surface are correlated in a one-to-one way with correlators outside the hidden surface. And that's the result. One gets a different answer from the answer that Hawking had. Okay, let me now go on to more recent things. Of course, this result that one has is also different from what's sometimes called the page curve. So I showed you a result which said that the von Neumann entropy is just a constant, and that's also not what we usually think of as the page curve. So Page famously argued that you look at the entropy of the radiation, that should actually go up and go down, and so this curve that we have is different from the curve that Page has. So what's the difference between this result that we have and the result that Page had? So the difference again arises because Page also assumed factorization. In fact, this is pretty manifest in the paper. If you look at the result that Page had, Page was speaking of a Hilbert space of dimension Mn, which is again separated into a subsystem of dimension M, another subsystem of dimension N. And then, Page computed the entropy of a subsystem. And of course, what this, if you do have factorization, this argument is completely correct. And non-gravitational systems must obey a Page curve, and they do obey a Page curve. In non-gravitational physics, the Page result is a very useful result. But in applying this to black holes, Page once again assumed precisely the same thing. He assumed that the black hole is a subsystem which has a dimension. The radiation is another subsystem which has a different dimension M. And these subsystems form a total system in a pure state in the Hilbert space with dimension Mn. So, there's explicitly once again an assumption of the factorization of the Hilbert space. And if the Hilbert space does not factorize, then there is no reason once again to expect that the entropy of the radiation will follow a Page curve. And that explains why the result that we have is different from the result that Page had, because Page once again explicitly assumed the factorization of the Hilbert space.
Suvrat, I have a question about
Yes.
this. Is it
Yes.
possible to assume some kind of, or to, let's try to parameterize the lack of factorizability? So if I do some like perturbative factorization, it almost factorizes, and then just cut that series off at some point, can you see that you do recover a Page curve from it?
Yeah, so I think, for gravity, it's very tricky for the following reason. You see, the point is, so you could say, let's say you had a non-gravitational system, like some set of qubits or something, right? And if you had a non-gravitational system and that evaporates, you do expect to see a Page curve for the non-gravitational. So, we live in a world where gravity is quantized. But if you have some piece of coal evaporating, you expect to see a Page curve. So what's the difference between, when can you ignore these effects and when can you not ignore these effects? So roughly speaking, if you want to make sense of the entanglement entropy, maybe I can write here, you need to keep track of terms of the order of e to the minus s. Let's see. E to the minus s is an important thing because can you see the e to the minus s? I just wrote e to the minus s. Okay, that's an important factor because typical microstates differ by that amount. So if s is the density of microstates, you need to keep track of terms of the size of e to the minus s. On the other hand, every effect that I talked about is suppressed by g Newton into e to the d minus 2 in d dimensions. So for usual non-gravitational systems, you take a limit where you take this to 0, where Planck scale goes to infinity, while you keep s finite. And that is the limit in which we usually work, right? We usually work in a limit where the density of microstates remains finite, but the Planck scale is just crazily deep. I mean, that's how the real world is. But for a black hole, notice this is not the case because g e to the d minus 2 is roughly 1 over s with some numerical constant that's not important. So you can't take a limit where you keep track of the corrections where you see what is important for the Page curve to go down, but you also throw away these effects. So you could of course define a coarse-grained entropy. You could say I'll just keep track of very simple degrees of freedom, and then you would see the Hawking result where the entropy just kept going up. But now you want to make it more and more fine-grained, and if you make it fine-grained enough that you keep track of the purity of the state, so you start keeping track of e to the minus s degrees of freedom, then you also can't forget about these effects that I'm discussing. So that's why these effects are important for black holes, but not for other systems. Okay, thank you. Okay, great. So thank you for that question. Great. Okay, great. So now I have 10 minutes left, or 5. Can I take like 10 minutes more or 5 minutes more? Is that okay?
Maybe 15 minutes.
Oh, great, fine. Great. So then I can go to this last. Okay, great. So great. So let me now, perhaps some of you are thinking, there's been a lot of activity on computing the Page curve of ADS black holes. There's been a significant activity on this in the recent literature. And how do these results relate to what I've been saying? So the first thing I should say is there's no contradiction between what I said and these results on computing the Page curve for the following 2 reasons. Because the models that have been used to compute the Page curve involve slightly non-standard theories of gravity, in fact, related to what Maulik said at the beginning. The first difference between what I'm saying and the models that have been used is that these models that are used to compute the Page curve, gravity is not dynamical throughout space. Rather, you have gravity in some part of space and then you couple it to a non-gravitational path. So, I'll say this in more detail once more, but there's this black hole, there's some gravitational boundary, which is this red line, and in this pink region is some non-gravitational path. And so gravity switches off at some point. And the second is that in all these computations, at least in higher than 1 + 1 dimensions, it turns out that the graviton in the theory of gravity has a mass, and so there is no Gauss law in these models. And so, the basic physics that I was using to make all these arguments was, in fact, the Gauss law, the quantum version of the Gauss law, the fact that the Hamiltonian was a boundary term, and that's not true in these models. And so that's the reason one does get a Page curve, and there's no contradiction in what I was saying and what one gets here. But I think it also means that these models, are not accurate models for black holes in standard theories of gravity. So let me say that in some more detail. So the first statement is, as I said, the way one sets up this calculation is one takes a black hole with asymptotically ADS boundary conditions. So this is the boundary of ADS, and in fact, what I was saying was that information about this, what we know from ADS-CFT, in fact, one doesn't even need to say anything about flat space. One already knows that information about the black hole is already available near the boundary of the gravitational region. We then couple this whole system to a non-gravitational path. So that's now we've added on this pink path to the system. When you do this, the whole system turns out to have a description where you can just forget about the gravitational theory as what's called a BCFT, a conformal field theory on the space with the boundary, where you just keep track of this non-gravitational path and this boundary of this ADS. So it's like some CFT coupled to a defect that lives at the end of the CFT. And then in this non-gravitational path, we make an imaginary interface, that's this dashed line, and then you compute the rate of information transfer across this imaginary interface in the non-gravitational path. But of course, because the computation that is being done is in this non-gravitational path, the Hilbert space factorizes because the Hilbert space of the path factorizes. As I said, the whole system on the right-hand side has a non-gravitational description. And then, there's no gravity. And of course, as expected, the information transfer across this interface follows the page curve, and the Hilbert space factorizes, and one does see what one expects to see. It is quite important, though, that the path is non-gravitational, and one of the checks that we first did with the group of 7 was to check what would happen if you were to turn on gravity in the path. I won't go through that in detail, but roughly the way that's done is that the way this path is added is by taking an EDS space and having what's called a charge triangle brane in that space. The way you would turn on weak gravity in the path is by introducing another brane in the system. And one of the results we found is that if the path is made gravitating, the page curve vanishes as one expects it should. And so it is, these calculations, the path is not just a spectator, it really is important for the physics. And these calculations are genuinely gravitational. And we should not think of them as measuring, information emerging from the black hole. What they're measuring is how does information flow from one side, one part of the non-gravitational path, to another part of the non-gravitational path. And if you turn on even weak gravity in the path, then this page curve does not remain anymore. But in fact, so this suggests that there's no contradiction between what I was saying and what's happening here. But in fact, if you look a little closer, you find that there is some tension between what I was saying and these recent proposals. And the tension comes from what's called, the main technical tool that was invented to do these page curve computations, which is called the island formula. So, I won't go into details of the island formula, but what it turns out to happen is that, so this is a picture of the same system that I had previously, except I'm now drawing a space-time diagram. So here is my EDS. This middle part is EDS. This is the boundary of EDS. This is a Cauchy slice in ADS, and this part is triangles on the right hand and the left hand side are the non-gravitational paths. And it turns out that at late times in these systems, part of the path is redundant with part of the gravitating spacetime. What that means is that the operators in this part of the gravitating spacetime are described by operators in one part of the path, and operators in the rest of the gravitating spacetime are described by operators in another part of the path. And one of these parts is called the island. This is the part marked in red, and that turns out to be redundant with this part of the path, which is called the radiation region in these computations. So this green region in the non-gravitational path describes the island in the gravitational region, and the blue region in the non-gravitational path describes the complement of the island in the gravitational region. But in particular, I was telling you in the first part of this talk that if you take a Cauchy slice in the theory of gravity, then the boundary of the Cauchy slice has all information about the bulk. But if this is true, that the blue region describes what's happening near the boundary of the Cauchy slice, and the green region describes what's happening in the island, then clearly, in the bath, there's a factorization of the Hilbert space. The blue region doesn't have information about the green region. There's microcausality in the bath. And so, it must be that this black region doesn't have information about the red region. So this is clearly in tension with what I said, because I was saying all the information is available near the asymptotic boundary of a gravitating spacetime, but here we find that that's not the case, because the island proposal explicitly tells us that the island and the complement of the island are described by different regions in the path which commute. So how is this resolved? The first thing we did in this paper we wrote with the group of 7 earlier this year is to point out that in fact the tension is not just with its principle of holography of information. You might say maybe we don't believe that, but in fact one can show that the puzzle arises within perturbation theory without using the full power of the previous result. So this is a point that I'd like to emphasize. Maybe you didn't believe anything I said in the first part of the talk. But what I'm saying now is just a simple perturbative calculation that shows that the island proposal would lead to a problem in perturbation theory if you have a theory which is based in a standard theory of gravity with the Gauss law. Okay. So let me first explain for those of you who let me first make an observation. For those of you who've worked with the Ryu-Takenagi formula and standard entanglement wedges, this is what we usually do in ADS. So this is the boundary of ADS, and we say we have some region, let's call this region R, and we draw this Ryu-Takenagi surface, and we say, in ADS, there's a notion of sub-region duality, which is that physics in this region R is dual to physics in this region in the bulk. And islands are also entanglement wedges, but usually entanglement wedges always have an asymptotic region. If you think back to every entanglement wedge you have seen in standard ADS CFT, it always has some asymptotic region. And the reason that's important is that, if you think of an operator inserted inside an entanglement wedge, you can dress it to the part of the asymptotic region that is inside the wedge, as part of the wedge. And that allows operators in the wedge to form a closed algebra, because they're dual to some part of the boundary whose operators do form a closed algebra. So it must be that operators in this part of the bulk also form a closed algebra. So this is how standard entanglement wedges work. But islands are unique in being the only known examples of entanglement wedges that are disconnected from the asymptotic region. So islands are not of this form. Islands are just some region in the middle that's just disconnected from the asymptotic region. Okay, so why is that a problem? Why is that a puzzle? So it's a puzzle for the following reason. The puzzle we showed is that, imagine that you have a black hole state, so here you have a black hole, and so the horizon is somewhere. The horizon is actually not marked. This pink region is the island. You can think of it as being, it actually extends a little bit outside the horizon. And so imagine that you have a black hole state of this kind in a standard theory of gravity. In a standard theory of gravity, the Gauss law does apply. So consider some black hole state with an island and think of a simple excitation. So I'm not going to do anything very complicated. Just think of a simple excitation. If you have a propagating field phi, then just take this unitary operator, take this field phi, smear it in some point near some point P in the island, and construct a simple perturbative unitary operator out of this field. This is a simple operator in what we usually call the code subspace or the little Hilbert space. And we usually think one can act with such operators in an entanglement wedge while leaving expectation values in the complement unchanged. I mean, this is what it, if we say that operators in the island are dual to some operators in the bar, then we better be able to describe like simple operators of this kind at least. And they should commute with operators which are outside the island, because those are dual to another part of the bar. But now we can actually do a simple computation. As I said, I want to emphasize this is a perturbative computation. You take this unitary operator and we compute the two-point function of the integral of a metric on this dashed line and the insertion of another scalar field of the same kind. It's just a two-point computation. One can just do this computation explicitly. If one does it, one finds some answer. And the main point is that in the absence of this unitary insertion, this correlator would have been 0. But in the presence of the unitary insertion, this two-point function picks up an expectation value. What this means is that this unitary operator inside the island is causing a change in the expectation value of simple correlation functions outside the island, which is in contradiction with the principle that simple unitaries inside an entanglement wedge should leave expectation values outside the entanglement wedge invariant. And if you see here, this is a result that appears at first non-trivial order perturbation theory. So this result appears with a single factor of G Newton. So if you were to take the limit where G Newton goes to 0, as we discussed previously, which is the limit in which we usually think of localized operators in a non-gravitational theory, this puzzle would not occur. But at first non-trivial order in perturbation theory, you get some puzzle, and that's the puzzle that we find here. It's perturbative, it's not non-perturbative. Okay.
So, can I ask,
yes.
Do you expect that this puzzle will remain if you could do some resummation to account for a full series of effects?
I think so, because how would you get rid of a first order term in perturbation theory by resummation? I mean, it's the first order term that you compute, so it wouldn't go to 0, right? How would you? You could
unless there's some flaw in the way that the perturbation series is working, that can't happen, but there could be.
You mean it could be that just perturbation theory breaks down? I mean, usually you think that perturbation theory is asymptotic, and there is a small parameter here. And this this term here gives you some energy scale. So this is G Newton times some energy scale. So the small parameter is G Newton times the energy scale, and usually you would think that perturbation theory is asymptotic, and so you correct it with non-perturbative corrections in the same path. But you would not usually think that just the first order term that you compute is wrong. I mean, maybe it is, but I can't think of any reason why the first order term would just be happen. I mean, there is a small parameter that you can use, which is G Newton times the energy scale you get from there.
Okay, that's a good point. Thank you.
Okay, so now, of course, in fact, it's not true. This doesn't mean that all the computations that have been done with islands are wrong. So in order to do this computation that we did, we used some property of how the metric correlators of the metric and fields inside, which holds in standard theories of gravity. It is in fact the property that the integral of the metric at infinity has a particular commutator with the field inside. It's a Dirac bracket that you can compute in the standard theory of gravity. The Dirac bracket is this, and this is in fact the statement of the Gauss law. The fact that you get this Dirac bracket comes from the constraints. It is a statement of the Gauss law. It's just a perturbative statement for our purposes, but it is a statement of the Gauss law. And in fact, there's no, the computations that people have done using islands are not wrong. And they're not wrong because they've all been performed in theories of gravity where this equation does not hold and the graviton is massive. So let me explain first why the graviton is massive and why this equation doesn't hold in massive gravity. Okay. So the first, let me first explain why the graviton is massive. So there's a very simple argument. There are many ways to see this, but in fact, these systems were analyzed many years ago. People forgot about it and then rediscovered them. But when they were analyzed many years ago, it was already understood why the gravitons were massive. So think back of this process that we had previously, where you had some ADS black hole. And before you coupled it to a bath, there was a stress tensor on the boundary of this black hole, just on the boundary of this ADST that is conserved. That's the stress tensor on the boundary is conserved. But now you coupled it to a bath, and so you allowed energy to leak out of this boundary of the gravitational region into this pink bath. And so by construction, the stress tensor is not conserved. You have to have some order 1 term here to allow the black hole to evaporate. But if you think of what this means in conformal representation theory, the fact that the stress tensor is conserved is a statement that, the stress tensor obeys a wadded entity is the statement that the stress tensor is in a short representation of the algebra. The fact that it's not conserved is a statement that it's in a long representation, and so it must have an anomalous dimension. If the stress tensor does not have the dimension of the boundary, that is the statement that the ADS-D graviton picks up a mass. So this argument, as I said, was understood many years ago when people thought about coupling ADS to baths by Aroni, Clark, and Cauchy in 2006. It's the simplest and quickest way you can see that coupling ADS to a theory with the bath forces the graviton in ADS to pick up a mass. Okay, now what's different about a theory with a mass and without a mass? Here's a very simple example. I'll say something more detailed, but let's just think of linearized gravity in flat space, in Minkowski space. Okay? So linearized theory of gravity, just let's take this Hamiltonian constraint and let's just linearize it. It's already enough to make the point. So it so happens that if you linearize the Hamiltonian constraint, you find that the metric fluctuation is related to the energy density that you insert at some point. And it so happens that this term on the left is a total divergence. And so in the linearized theory, you already see that because this is a total divergence, if you integrate both sides, the right-hand side and the left-hand side, If you integrate the right-hand side, you get the total energy density. And it tells you the left-hand side, you get a surface integral. So this is the linearized statement that a surface integral gives you the total energy density. We can think of the same constraints that apply in a theory of massive gravity. Now you find that some derivative of the metric plus this term, which is m squared times the trace of the metric, is equal to the energy density. But the left-hand side is not a total divergence. Consequently, in a massive gravity theory, the Hamiltonian is not a boundary term, and we do not have a Gauss law. So you cannot measure the energy from infinity in a theory of massive gravity by virtue of this very simple difference that you already see in the linearized theory. And so the Gauss law doesn't apply, and so certainly everything else that I was saying about the holography of information does not apply. So this is a simple example, but in fact, we can see that islands are explicitly consistent in the so-called doubly holographic Cauchy models that have been used to study islands. But it's also true that these models always involve massive gravity. So let me just say that in some more detail. So, the way a lot of these island computations have been done is by taking a theory in higher dimensional ADS and by putting a brain in this, as I said. So here is it's the same system I was showing you earlier. This is the green part of this bath. This is the blue part of the bath, and this is the gravitational region, now realized as a brain in the higher dimensional ADS. In these setups, the island rule just reduces to the usual Ryu-Takenagi prescription. You want to compute the entropy of part of the bath, you just do the usual Ryu-Takenagi prescription. That's this purple line here, and then you compute the entropy the way you do usually. And clearly there's no inconsistency. This is the usual Ryu-Takenagi prescription. But you see, there's also not really an island in that this red region that we call the island is now actually connected to asymptotic infinity through the extra dimension. And there's no puzzle because this is a standard entanglement wedge. But it's also true that the theory of gravity on the plane is massive. And in fact, when Cauchy and Randall first analyzed these models back in 2000, as I said, people forgot about them and then remember them again. They already noted that the d-dimensional effective theory of the brain, the massive theory, was a massive. The theory of gravity was a massive theory. So one can, in fact, realize this intuition that I said about the constraints more explicitly. One can take the constraints in this higher dimensional ADS and dimensionally reduce them. And one finds that they have the form, precisely the form that I indicated in the linearized theory. One finds that they look like divergence of some current on the brain, plus some term that looks like m squared times the trace of the metric fluctuation is equal to the energy density on the brain. This extra term that you get, this massive m squared term, corresponds to the fact that the gravitational field on the brain can run off in the extra dimension. You can take a particle, even in, and you can make the gravitational field run off in this extra dimension. From the point of view of the brain world theory, that running off in the extra dimension is realized as a mass for the graviton. And so once again, you see in these models quite explicitly that in the brain world theory, the constraints do not have the form of total divergence is equal to mass density. And so the energy is not computed by a boundary term. It's kind of obvious in the setup. The energy on the brain is not given by doing an integral in this part where my mouse is. To compute the energy, you need to do an integral of the whole boundary. So there is no term at the boundary of the brain that knows about the energy everywhere in the brain. And that's realized explicitly. That's consistent with the fact that the theory on the brain, the theory of gravity on the brain is passive and does not have a Gauss. That's why these island computations are consistent, and they're consistent because the mass of the graviton is pretty crucially important for these computations too. But it does mean that if one thinks of standard theories of gravity where the Gauss law applies, then one would not expect that islands give us an accurate picture of what is happening. Okay, so let me just conclude. I think I'm maybe a little bit over time already. I said that standard theories of gravity store quantum information very differently from local quantum field theories. This can be shown precisely in some settings. I gave you an example in Minkowski space, 4-dimensional Minkowski space, asymptotically Minkowski space, which was a non-perturbative algebraic argument that one can set up to show that all information is available in the past boundary of future null infinity or the future boundary of past null infinity. There's a more perturbative hands-on analysis that one can do in ADS to show how theories of gravity store quantum information very differently from local quantum field theories. And I think this can be used to understand why gravitational theories are holographic whereas non-gravitational theories are not. So theories which have islands, do not obey this principle of holography of information. It's because the information in the island is not available near the boundary of the gravitational region. That's why it is an island. But islands are inconsistent in standard theories of gravity, where the Gauss law applies. But islands are consistent in specific theories of massive gravity, which indeed are the theories which have been used most often to analyze these things. Okay, so that's all I had to say. So thank you for your attention. I'll stop here.
Thank you very much. Now we may take some questions from the audience.
I had a couple of quick questions, and I have to go as well. So maybe let me just quickly answer. My question will be more naive. I don't know about the technicalities. But what if nature has several flavors of particles? So, for example, you can imagine a U1 cross U1 model.
Yes.
And the bulk has either photons of the first U1 or photons of the second U1.
Yes.
Can the boundary tell us what kind of photons there are inside?
Yes. Thank you for asking the question. Let me share the one for you. I almost could have planted this question, but so let me take the two particles, right? So let's make an excitation here, and one excitation is e to the I phi 1 acting on the vacuum, and let's relate these things by a global symmetry. So I'll just use scalars, but we can think of photons here.
Okay,
so
sure.
Here is the state 1, and here is the state 2. So and you can smear it with some function f. Where this function f is somewhere here, and now you ask me, I want to make observations near the boundary to determine whether it's state 1 or state 2.
Mm-hmm.
And these states are related by global symmetry, so they have exactly the same energy.
Mm-hmm.
So the correlators that will distinguish between them are the following: h phi 1. You can check that this will pick up a non-zero expectation value in the state 1, which has an excitation of 1.
Mm-hmm.
Whereas 1 h phi 2 is equal to 0. I can write down what this correlator is. It will it'll give you it'll roughly give you the 2-point function. It'll give you so 1 h phi 1 will roughly give you phi 1 dot phi 1. You can check in perturbation theory. Whereas 1 h phi 2 will give you 0. Conversely, in the state 2, this correlator will have some expectation value, whereas this correlator will be 0. So notice I'm breaking the symmetry by measuring not just the energy, but correlators of the energy with other dynamical degrees of freedom. So even though the states were related by a global symmetry, this simple 2-point function can distinguish between them. These are very simple states. You could make it harder for me and force me to use higher point functions. But this is already, these states are completely indistinguishable in a local theory because this is a unitary operator that's acting here. And so the unitary operator would leave every expectation value in the non-gravitational theory, space like separated invariant. But even though it's a localized unitary operator in a theory of gravity, you can distinguish between these two states by means of these 2-point functions. You get a factor of G also. Is that clear?
Well, that's, I get your answer that you can, and maybe I'll have to think about the argument
It's
itself.
a pretty simple computation. You see, all you need to do is just expand this out to first order in perturbation theory and use the fact that h phi 1 gives you phi 1 dot. That's just a Dirac bracket you need to compute. So if you just expand the state out, this unitary operator out on both sides, you will see that you will get a Weightman function of phi 1 dot with phi 1. This is to first order in this parameter lambda.
Yeah, that is quite remarkable that gravity can distinguish flavors. But yeah, okay, let me think about that.
Okay.
All right, I better leave. Thanks a lot.
Okay, thank you.
Thank you.
Can I ask you a question
Yes.
again about the ENM analogy that I asked about earlier?
Yes.
So you said the distinction between gravity and ENM is that in ENM you can don't have, the dressing doesn't have to go off to infinity because you can find you can find gauge invariant quantities that because of the existence of positive and negative charges. Is that right?
Yes. Yes.
So it's a bit, so that's a feature of the sources of the theory. Is that right? I mean, it's not, doesn't seem to be an intrinsic feature property of ENM. Are you saying that because the sources are?
You know, it's the fact that, so in the argument, you know, I use, so let me say it another way. I use the you know, this argument I gave you, I use the projector on the vacuum.
Okay.
So you could ask, you know, let me project onto states of zero charge. That's an infinite set of states. There is no one state which has zero charge. In fact, you know, if you project onto states of zero charge, it will almost do nothing to the physics of the part. So what is special? Maybe another way to say it is that in gravity, from infinity, you can project onto a specific state, which is the vacuum. So let's forget about vacuum beginners. So let's think about ADS. It's a simple set. Then at infinity, there is an operator in the theory which allows you to project onto a specific state, which is the vacuum. And that operator is the projector on the vacuum, which is just, you know, a function of the boundary Hamilton. There is no similar operator in the theory in ENM or in any gauge theory. Because there's, and that's a function of the fact that, you know, there is an infinite number of states which have zero charge because you can have both positive and negative charge.
So explicitly, if I try to couple ENM to say an electron field,
Yes.
you're saying that it's not just a vacuum that has zero charge, but I can take any combination of the same number of positrons and electrons, and so
Exactly.
yeah.
Exactly.
So
there's no way you project exactly. So, you know, correspondingly, of course, F squared is gauge invariant, but you can also take an electron and take a Wilson line and make it end with a positron, and that whole operator is also gauge invariant.
Right.
So now, you know, so that just commutes with everything at infinity. You can't detect whether or not you insert it or not.
Okay. Now, another statement that that's often made is that there are no local gauge invariant operators in gravity because of diffeomorphism invariance.
Yes.
Whereas here you really used sort of only Gauss's law. If I'm, can you connect it? How are the two related?
No, I think they're very closely related statements. So, you know, it's really Gauss's law that, I mean, the important thing of diffeomorphism invariance is the Gauss law. It's the fact that why there are no local gauge invariant operators, because the charge is the energy, and to have zero energy, you need to have infinite delocalization. And to make a gauge invariant operator, you need to make it commute with the Hamiltonian. But, you know, so it has zero energy. But to do that, you know, by the uncertainty principle, you need to have infinite delocalization. So it's very closely related to this statement. But, you know, yeah. So it's, I mean, these are very closely related statements. There's no local gauge invariant operator, and the information is available to infinity. Although somehow, people are happy with one, but not always happy with the other.
No, but in ENM, you don't have the diffeomorphism invariant story. So the argument would be that you can get, you don't have to have this delocalized states because you can.
Because there's no uncertainty principle for the charge. You can have something of zero charge, which is localized. There's something of zero energy, but the uncertainty principle has to be infinitely delocalized in space. So you know that you can have something of zero charge, which is just sitting in a small box. But you can't have something of zero energy that's sitting inside a small box.
Yes. Right. Okay. Good. Thanks. A very nice talk, by the way.
Thank you.
Any other
I also
questions?
have a couple of questions. So my first question is, what happens if we didn't have access to Scri Plus? Because the way that you're building this up, we actually need an asymptotic boundary in order to get complete information localized somewhere. So what if I only had access to, say, to some cutoff surface? You know, let it be asymptotically far away from anything interesting going on, but I don't want it to actually be at asymptotic infinity.
Yeah, I think we would still be able to make the argument if you had access to an entire sphere, but you know, it's much harder to make the argument precise because just because of all of these issues, you know, we don't. So one would to make the argument. So I think morally the argument should go through, but it's much harder to make it precise because you know one would need to somehow analyze gravity with finite boundary conditions and then you know, keep track of the fact that so it just the whole thing just becomes messier. You know, when we say that information is available at a finite region, but I think that, one should be able to say something. Maybe at least in perturbation theory, one should be able to say something, but it's technically harder to do. Yeah, so my suspicion is that the argument would go through, but the analysis would be technically much harder to do in finite information. It's the statement that, we say that in general relativity also we don't have a local definition of energy, and you only define energy at infinity. But okay, usually we are happy to not go off all the way to infinity, but go off some distance away, and say so presumably it works the same way. But it would be it's always hard to make that precise in some setup.
Okay, I have I think that sounds totally plausible to me. I do have another question just to make sure I understand making about islands in massive versus massless gravities. It seems to me like you're saying that in massive gravities, they are actually factorizable in this sense of some spatial factorization, and that's why the islands are working there. Massless case, not factorizable. The island picture is really doing the wrong computation, but also only the massless ones are actually obeying a holographic principle. Is that right?
Yes, I think so. That's right. So I should make one caveat. When we say massive theories of gravity, we don't really understand massive gravity very well, but in these large-scale models, in these cases, it does look like they're factorizable. What happens in general theories of massive gravity, we don't know. But at least in these examples, it looks like they're factorizable.
So the factorizability property is more important than the massive versus massless. It's just that the two are correlated as far as we know.
Correct.
Effectively, you just need a sort of a time-like propagation, right? So that there are degrees of freedom that don't land up on Scri+. That's what massive buys you?
No. So it's not just that there's massive matter; it's that the graviton is massive.
Yeah.
So it's more that right. So if the degrees of freedom that don't land up on Scri+ and there's massive matter, then you would still believe that the Hilbert space doesn't factorize because of the gravitational property. But if the graviton is massive, then it's really very different. Then you can't measure. There's no Gauss.
Exactly.
Yes.
Even if there were massive matter, the Gauss's law on gravity will transmit that information to infinity. But if the graviton were moving in a sort of, well, geometrically speaking, if the gravitational degrees of freedom were able to end up on I+ rather than Scri+, then that would not be captured.
Exactly. Thank you. Yes.
Okay, I've got one last question. So from the amplitude story about the double copy that I can take a gauge theory and appropriately square its amplitudes to get a gravity theory, how can I see this difference arising from that perspective, or can I?
That's a good question. I don't know what the answer to that is. Let's see. I'm not sure how to see the answer to that from this perspective. In the S matrix picture, this is the statement that you make some. So you make some. It must, it has to do with the fact that when you have soft gravitons, you pull out the energy. So particular kind of soft gravitons in an S matrix will pull out the energy, but they'll always pull out a positive term, whereas particular kind of soft gravitons in E and M might pull out the charge, but they could pull out positive and negative charges. I'm tempted, so somehow you have to make that important. Like it's the fact that so there's a so you could think of this whole story in terms of S matrix elements. I was speaking in terms of correlators and Scri+, but those are just Fourier transforms of S matrix elements. So this is the statement that a particular set of S matrix elements plus some soft insertions determine the full S matrix. But they should not determine the full S matrix in base series. But I don't know how to make that precise. It must rely on this difference, which is the fact that the energy is always positive in gravity and not always positive in base series. But I haven't thought about that. It's an interesting question. Maybe I'll think about it if I have something to say. I don't have immediately relation to the story.
Actually, Cindy's question is sort of part of why I asked the thing earlier about large and small gauge transformations, because in the double copy picture, you can, I believe, map those memory effects. But with respect to S matrices, you can think about soft limits of S matrices as being equivalent to memory effects. I think that was the 2014 paper. by Straminger and company.
Yeah, right. But please go on, please. But how do you see from that the difference between these setups, or do you?
I don't know actually. That's what I was wondering if it's possible. Because clearly some of your arguments are based on something similar to these soft theorems, but
yeah, I agree. It should be possible. I don't know how to relate it immediately to the double copy story. Also, the double copy story is a little bit, it's a little, okay. I don't know how to relate it immediately. Maybe there's a relation. It's an interesting point. From the Hilbert space perspective, it's kind of clear why there's a difference, but from the amplitude perspective, I don't immediately see. But yeah, there probably is a good way to understand it. But I don't know what it is.
Okay, thank you.
Thank you. Do you have more questions?
Yeah, I have a question. Have you thought at all about how any of this looks like in, say, de Sitter space, where the panels are?
Yeah, that's I have thought, but I don't have anything sharp to say about that as well. So there are yeah, that's also a very interesting question. And we thought about it, but I don't have anything sharp to say about how it works. But it's a very natural, very interesting question. Right?
Do you have more questions? If no, let's thank Suvrat again.
Thank you.
Thank you very much. See you.
Bye.
Okay, so see you then.
Bye.
Thank you. Thank you.
Nice talk.
Yeah, thanks so much, Suvrat.
Thank you. Thank you. Yeah, see you. Bye.